Let's go ahead and work some problems. We're going to combine all the concepts together, okay? Just limiting reactant, access reactant, percent yield, all of it. First up, Jessica synthesized aspirin, C9H8O4, in the lab. She used 4.597 grams of salicylic acid, C7H6O3, and 9.56 mils of acetic anhydride, C4H6O3, density of 1.08 grams per mil. At the end of the lab, she calculated a percent yield of 72.3%. What is her actual yield? Now, in a reaction like this, I would not expect you to know the balanced reaction. I would give it to you, okay? But so for your knowledge, the reaction is it's salicylic acid, which is C7H6O3. This reacts with acetic anhydride, C4H6O3, which is a liquid, and it produces what we call salicylic acid, acetyl salicylic acid, common name aspirin, and aspirin's easier to say than acetylsalicylic acid. And that's a solid. And then it produces acetic acid, CH3COOH. Okay. So this is the reaction, and it's all 1-to-1, which is a nice little part there for us. A little less work there. Okay. First up, I don't actually know what my limiting reactant is. I know that I've used up 4.597 grams of this, and I've used up 9.56 mils of this, and the density here is 1.8 grams per mil. So I'm going to figure out how many grams of the acetic let's see, what did I write down? How many grams of salicylic acid, C7H6O3, are needed to react all of my acetic anhydride. So I've got 9.56 mils of the C4H6O3, and this has a density of 1.08 grams for every 1 mil. Notice I'm intentionally writing down the unit of what I'm looking at right next to the species because it's going to get really confusing really fast otherwise. The only difference between these two things is this 7 versus the 4 here. I need to be writing down exactly what I'm looking at. That cancels my mils and gets me into grams of the acetic anhydride. So now I can go ahead and convert to moles. 1 mole C4H6O3 weighs 102.1 grams. Now that I'm in moles of acetic anhydride, I can convert to moles of salicylic acid. So 1 mole C7H6O3 is consumed for every 1 mole C4H6O3 consumed. So they consume each other in a 1-to-1 mole ratio. Definitely gonna run out of room there. So convert that to grams of the salicylic acid, 138.1 grams C7H6O3 for every 1 mole C7H6O3. This gives me an answer here of 14.0 grams of C7H6O3. What does that mean, though? What does that 14 grams mean? What that means is to react all 9.56 mils here, I need 14 grams here. I don't have 14 grams. Therefore, this is my limiting reactant, and this is my access reactant. So I don't have enough, therefore I now know what my limiting reactant is. Now I can use that to determine how much aspirin I can actually make. So the number of grams of the acetylsalicylic acid I can make, or the aspirin, C9H8O4, is dependent upon the amount of salicylic acid reacted. 4.597 grams C7H6O3. Convert that to moles. 1 mole of the C7H6O3 weighs 138 0.1 grams. One mole of aspirin, C9H8O4, is produced for every 1 mole of salicylic acid consumed. And now that I know moles of aspirin, I can go to grams of aspirin. Aspirin is 180.2 grams of C9H8O4 for every 1 mole of C9H8O4. Based on this, I can make 5.996 grams of C9H8O4. So I can make just under 6 grams of aspirin under these conditions. That didn't totally answer the question, though. The question is saying, at the end of the lab, she calculated percent yield of 72.53%, or 72.3%. I apologize. What is her actual yield? So percent yield equals actual yield divided by your theoretical yield times 100%. We're told her percent yield is 72.3%. This equals what we're trying to solve, which is her actual yield over her theoretical. Again, your theoretical is what you've just calculated. Theoretically, you can make this much. So 5.996 grams, C9H8O4 times 100%. And if you solve that out, you should get 4.34, just 3 sig figs to the 72.3, 4.34 grams C9H8O4, also known as acetylsalicylic acid, also known as aspirin. So kind of working your percent yield, just working it backwards. What about the next example? Solid red phosphorus, P4, reacts with bromine to form PBr3. If 35 grams of bromine react with an excess of P4 and 27.9 grams of PBr3 are formed, what is the percent yield? Okay, so solid red phosphorus, P4, reacts with bromine. I know bromine is one of my diatomics. Bromine is also one of the only 2 elements on the table that is in liquid form. And this is forming PBr3. Let's balance this. We have 4 phosphorus on the reactant side, so I need 4 on the product side. That gives me 12 bromines on the product side. I need 12 on the reactant side. Okay, I've got 35 grams of bromine with an excess of P4. That's nice. That's telling me that I don't have to deal with the limiting reactant problem. And my actual yield is 27.9 grams here. It's telling me this much was formed. So what's my theoretical yield? How many grams of PBr3 could I form theoretically? If I react all 35 grams of Br2, 1 mole of Br2 weighs 159.8 grams. Again, bromine itself is 79.9, so times 2, 159.8 grams. The reaction tells me that 4 moles of PBr3 are produced for every 6 moles of Br2 consumed. And when I add up the mass of PBr3, 3 bromines, so 3 times 79.90 plus 1 phosphorus, phosphorus is 30.7, I get a molar mass of 270.7 grams for every 1 mole of PBr3. I do have 35.0, which is 3 sig figs, so my final answer should be 3 sig figs here. So 39.5 grams PBr3 is my theoretical yield. Go ahead and calculate percent yield. Remember, your percent yield is your actual yield over your theoretical yield times 100%. So 27.9 grams over 39.5 grams times 100% gives me a value of 70.6%. My percent yield in this question is 70.6%. So not too bad. Okay.
Chlorine gas reacts with aqueous potassium bromide to produce aqueous potassium chloride and liquid bromine. Assuming a complete reaction, determine the percent yield if 200 grams of chlorine gas reacts with excess potassium bromide and produces 410 grams of bromine. So first thing we need is that balanced reaction. So we've got chlorine gas. Chlorine again is one of our diatomics, so we've got Cl2. It reacts with aqueous potassium bromide. Again, potassium bromide, potassium is an alkali metal, group 1, so always a +1 charge. Bromide is one of your halogens, group 17, always a -1 charge, so it's a 1-to-1 ratio. And aqueous means dissolved in water. This produces aqueous potassium chloride. Again, we know potassium is K+. Chloride is also a halogen, group 17, like bromine, so it will be KCl. And then liquid bromine. Bromine is one of our diatomics, so we have to remember to put Br2 here, and it is a liquid. We do need to balance our reaction, so I have 2 chlorines on each side and 2 bromines on each side, giving me also 2 potassiums on each side. Now that I've got it balanced, let's see, what do I got? Percent yield, if I react 200 grams of chlorine with excess potassium bromide. And my yield, my actual yield here, is 410 grams. Well, let's get to it. I need to know how much bromine I could actually make, theoretically. So what is my theoretical yield? It's based on how much chlorine I'm reacting, because that's my limiting reactant. So number of grams of Br2 that can be produced if I react all 200 grams of Cl2. Have to convert to moles first. 1 mole of Cl2 weighs 70.90 grams. Again, that's from the periodic table. Chlorine is 35.45, so 2 of them is 70.90, keeping my 4 sig figs. Looking at my balanced reaction, I see that 1 mole of Br2 is produced for every 1 mole of Cl2 consumed. And if you ever get stuck where you're at, start making sure your units are canceling. Your grams of chlorine have canceled, your moles of chlorine have canceled. You're now into moles of bromine, so now you can go ahead and use the molar mass of bromine. 1 bromine atom is 79.9 grams per mole per the periodic table, so 2 of them would be 159.8. And that is grams of Br2 per mole of Br2. Calculate this out, and you're going to get 451 grams of Br2. And again, that is your theoretical yield. Three sig figs, because my 200 with that decimal place on the end had 3 sig figs. This had 4 sig figs. This had 4 sig figs, so my final answer just has 3 sig figs. Now I just need my percent yield. Again, your percent yield is your actual yield over your theoretical yield times 100%. My actual yield was 410 grams because it says produces 410 grams of bromine. My theoretical yield was 451 grams of bromine. multiply that by 100%, and I get a yield here of 90.9%. So my percent yield here, 90.9. And our last question in this section, aluminum metal reacts with oxygen and gas to form solid aluminum oxide. If 2.5 grams of aluminum reacts with 2.5 grams of oxygen to produce 3.5 grams of aluminum oxide, what is the percent yield of aluminum oxide? Well, let's figure it out. We've got aluminum metal. We know aluminum is Al, and metals, unless it's mercury, is a solid. It's reacting with oxygen gas. Oxygen is one of our diatomics, so it is O2. It's forming aluminum oxide, and I will tell you this is a solid for aluminum oxide. So aluminum, again, always forms a +3 charge, no exceptions to that. Oxide means oxygen in its ionic form, which forms an anion. It's a nonmetal, so it does form a 2- charge. That's part of group 16. So the balanced formula here would be Al2O3. Balance this out. I recommend doing the oxygens first. You've got that 2-3 ratio going. You're going to have to get rid of that. So put a 3 in front of the O2 and a 2 in front of the Al2O3. That's going to cause me to put a 2 in front of the aluminum over here as well. Now, I don't know what my limiting reactant is here, so I'm going to have to figure it out. So I am told I have 2.5 grams of each reactant. And my actual yield here is 3.5 grams of my aluminum oxide. So I'm going to see how many grams of aluminum do I need to react all of my oxygen. I have no idea. Let's see. I have 2.5 grams of O2. 1 mole of O2 weighs 32 grams. Again, because it's O2, it's a diatomic. I look at my balance reaction. You know what? Let's actually balance that correctly. 4 aluminums. I'm looking at that, and I'm like, wait a minute. Yeah, we definitely need 4 aluminums there. So please fix that. There should be, because of the Al2 here, you need 4 of those. So 4 aluminums are used up for every 3 moles of oxygen used up. Four moles of aluminum for every 3 moles of O2. Now I've got moles of aluminum. I can go to grams of aluminum. I look at the periodic table and I see 26.98 grams of aluminum for every 1 mole of aluminum. And this gives me 2.8 grams of aluminum. This is what I would need. This is what I have. I don't have enough. So because I do not have enough aluminum, my aluminum is my limiting reactant and my oxygen is my access reactant. But now I know what value I can use to go ahead and figure out my theoretical yield. I need to use my aluminum to figure out my theoretical yield because that's going to limit how much product I can actually make. So my number of grams of aluminum oxide are going to be controlled, the amount of grams produced will be controlled by the 2.5 grams of aluminum reacting. Convert to moles. Can't compare grams. 1 mole of aluminum weighs 26.98 grams. Now I'm in moles of aluminum. Now I can use my balanced reaction to go to moles of aluminum oxide. 2 moles of Al2O3 are produced for every 4 moles of aluminum consumed. Again, if you ever need to check it, grams canceled, moles canceled, moles canceled. You got grams. You can do the same thing down here. My grams of aluminum have canceled, my moles of aluminum have canceled. I've got moles of aluminum oxide here. Add up the moles of aluminum oxide. Aluminum is 26.98 grams per mole, and I have 2 of them. Oxygen is 16 grams per mole, and I have 3 of them. So overall, I get 101.96 grams of Al2O3. If you really want to round it to 4 sig figs, you can. It doesn't much matter as long as you have at least 4. But if you did round this, it would be 102.0 grams of aluminum oxide for every 1 mole. And this will give you 4.72 grams of Al2O3. Again, that is your theoretical yield. That's how much I could make if all of my aluminum reacted and produced aluminum oxide. Just a reminder, checking sig figs here. I have 2 sig figs here, so I need 2 sig figs here. I have 2 sig figs here, 4, 4, 4. I need 2 here, so I should be rounding this to 4.7. And so we need to pay attention to that in our next calculation, okay? So 4.7 is what I should have for my theoretical yield. Your percent yield is equal to your actual yield over your theoretical yield times 100%. My actual yield here is 3.5 grams. My theoretical yield is 4.7 grams. I multiply that by 100% to get into percent form, and I get a final answer here of 74%. So based on these reaction conditions, if I actually got an actual yield of 3.5 grams, my percent yield would be 74%.